So lateral resolution is the ability to see two structures at minimal distance side by side, perpendicular to the beam. On your boards, they're going to expect you to know a lot of things that will improve lateral resolution or a lot of things that degrade it. But what they won't expect you to know is they could, instead of saying what improves lateral resolution, they could say things like what improves angular resolution, or what improves transverse resolution, or what improves azimuthal resolution. All these names here mean the same thing, which is lateral resolution. They could even say, what improves lata resolution? So anytime you hear the word angular, transverse, azimuthal, you need to think lateral resolution. Then you can kind of like put together all the things that improve it. So if they ask you, which of the following will improve angular resolution? You're going to think, well, that's lateral resolution. And then you're going to try to think of all the things that improve it. The first thing is high frequency. Anytime you have a high frequency, that means you have a large diameter, thin PZT crystal. The second one, the beam width, the more narrow the beam width, the higher our azimuthal resolution, transverse resolution, and angular resolution. Imaging at the focus, and this corresponds with the beam width. These are all the things that will improve lateral resolution. A lot of times, beam width will pop up. Beam width is what determines lateral resolution. So here's the transducer, right? Or the crystal. Here's the beam that's exiting the transducer. And what it does is it converges to the focus and then it diverges. Right here is where your lateral resolution will be the greatest because your beam width is at its narrowest. So here, this is where the lateral resolution will be the greatest because the beam width is narrow, as well as right here. Just always associate beam width with lateral resolution. And don't confuse beam width with elevational resolution. So the beam width is what determines lateral resolution, and the way you can get your beam width to be at its narrowest, you use a high frequency. You crank up your frequency, your operating frequency, not the pulse repetition frequency, your operating frequency. That will narrow your beam. The way we get a high frequency, you use a large diameter, thin PZT crystal. That will allow your beam to be at its narrowest. So here I listed imaging at the focus. That will improve lateral resolution. Line density. One of the things that improves lateral resolution is a high line density. And high line density simply means we just have a lot of lines compared to this one, which has a low number of lines. Line density kind of has two definitions. The first definition is the number of lines you have per frame, not per second. Let's say you get a frame, you freeze it, that frame will have a certain number of lines on that frame. Second definition is the space in between these lines. When we have these two diagrams side by side, this one clearly has less lines than this diagram. That means that the line density here is lower than here. This has a higher line density because it has more lines per frame. This is the line density you will want when you want to improve your lateral resolution. Each line is created by one pulse. So this represents a transducer with 5 lines, which means it took 5 pulses to create this image or this sector. The next is a multifocus. When I said that each line is created by one pulse, you can use an option to add a focus. That means that you're going to add another pulse to each scan line, meaning you'll have more than one pulse per scan line. Multifocus is a great way to improve the quality of your image. Look at this image here. You see those little triangles? These are foci in this image. When we compare this diagram to this diagram has one focus, meaning one pulse per scan line. This diagram has 3 focus or 3 foci per scan line. This image has 4. So this is a great way to improve lateral resolution. But when you hear multifocus, all they're doing is they're adding another pulse to the scan line. You'll have to know the types of transducers that have the best lateral resolution. This is a diagram of a linear, sequential, or switched transducer. And a linear means that the pulses go straight down, all the way down to the far field. The advantage of a linear is that you're going to have consistent lateral resolution going all the way down. It doesn't change. And these types of transducers are best for superficial imaging. As opposed to right here, Do you see how the line density gets farther and farther apart as it
Mm-hmm.
progresses in the far field? That
Mm-hmm.
means the lateral resolution will be poor in this diagram, but really good in this type of sector. So a linear will create a rectangular type sector. For your boards, they are just going to consider it linear, unless they literally say linear sequential or linear switch or linear phase. Then the other three things, a dynamic aperture is a great way to narrow the beam at various depths. If we look at this diagram here, do you see these little red rectangles here? These represent a PCT crystal, and each crystal is attached to a wire. If we look at these little teardrops here, this just represents the voltage coming down to stimulate these crystals. You can see that there are 1, 2, 3, 4, 5, 6, 7, 8, 9 crystals. If you just use your imagination, this is equivalent to one large thin crystal. And as a result, we're going to have higher frequencies. If we start off with all the crystals firing, this will represent a large thin crystal, which means we're going to extend our focal depth. The focal depth is anywhere from the beginning of the transducer to the focus. You could also say this is the near field or the Fresnel zone. But really, we're extending the focus deeper into the tissue. We're increasing our penetration. That's exactly what happens when you increase your frequency. You extend your near field or your focal depth, but your penetration does not increase. In fact, your penetration decreases when you increase your frequency. That's why we have this dynamic aperture, because to make up for the penetration, this helps us extend it into the far field. If we're just talking about high frequency, if we increase our frequency, that means that we're going to image more shallow and our penetration decreases. But with this dynamic aperture, we can extend the Fresnel zone or the focal depth to change the focal or the focus at this level here. If we shut off the outside crystals, that means the size of our crystal gets smaller. And as a
Okay.
result, our focal depth decreases. So here we have a large crystal, essentially, and our focus is penetrated more deeper in the tissue. Here we shut out the crystals, so we're using a smaller crystal, which means our frequency decreased, essentially, and our focal depth decreased, meaning our focus has moved closer to the transducer. Dynamic aperture, the reason why it's so valuable and the reason why it improves lateral resolution is because it's going to change the focus at various depths. So here, if we continue to shut off the outside crystals, our focus is right about the middle here. And then if we again continue to shut off more crystals, and we're left with 3 crystals, we are bringing our focal depth, or we're bringing the focus closer to the transducer. The machine or the transducer is shutting off these crystals so that we can change the focus at different depths. The whole point is to make lateral resolution the best at these different various depths. If we start over, we have all the crystals firing, and which extends our near field, and the focus is right there. That's where our lateral resolution will be the best. If we shut
Mm-hmm.
off the outside crystals, focus will be right there, which means our lateral resolution will be best right there, and no longer right here. If we continue to shut off the crystals, our lateral resolution will be the best right here, and then in this image right here, our lateral resolution will be the best right here, because we shut off these crystals. When we use all the crystals, it's essentially the same thing as high frequency, but in reality, when you increase your frequency, not using dynamic aperture, you're going to decrease your penetration. So ultrasound can't penetrate the higher your frequency goes. When you increase your frequency, your penetration will go down. When we increase our frequency, our operating frequency, our penetration will decrease. So it would look like this. This is a great example of a diagram that shows what happens when you increase your operating frequency, because your focal depth or your focal length will increase when you increase your operating frequency. The reason why your focal depth increase is because with higher operating frequencies, we're using a larger thin crystal. When we use a smaller crystal, what's going to happen is our focal depth or focal length, our near field, and our Fresnel zone will all decrease. And what happens is, because it shortens the near field or the focal depth, your far field is going to extend out more extreme like this, and our penetration will decrease. But we like high frequency. High frequency is good because it increases our axial and lateral resolution. So we add this dynamic aperture so that we can change the penetration no matter how high our frequency gets. So to start off, when you have a high frequency, your penetration goes down. But then when you add a dynamic aperture, you can change your penetration no matter how high your frequency is. Because of higher operating frequencies, beam diverges more in the far field with small crystals. The near field focal depth Fresnel will decrease because of the lower frequencies. Other things that improve lateral resolution are dynamic focusing and thin half-value layer. To sum up this part, when they ask you on your boards, how do you improve lateral resolution? First, you're going to look for beam width. You want to narrow the beam width, a narrow beam width. If that's not an option, then you look for high line density. That just means we have more lines. This is a low line density. Multifocus or add a focus. Sometimes they won't just say multifocus, they'll just say add a focus. Of course, using a higher frequency, which means you have a large diameter and a thin PCT crystal. Once you learn all the things that improve lateral resolution, it's pretty easy to know what degrades lateral resolution, because a lot of times, well, a lot of things that improve it, you just think the opposite, and that will degrade it. The things that degrade it are a low line density. This is the low line density. If you use a low frequency, meaning operating frequency, this has nothing to do with pulse repetition frequency, which means you're going to have a small diameter crystal and or a thick PCT crystal. Here's another interesting point. When you increase the depth, you will actually degrade lateral resolution. This is a huge advantage for you to know for your boards. Wouldn't that make sense if the opposite would improve it? So if you decrease the depth, probably not. Decreasing the depth wouldn't really change or improve lateral resolution because you're just taking the distance here in the far field and just shifting it up. So it really wouldn't change it. But if you increase your depth, yeah, it would definitely affect it. Makes sense that the distance gets farther and farther apart as you spread out. And then a thick half-value layer, which we'll talk about. So if they said, how do you improve transverse resolution? You're going to look for narrowing the beam, high line density, out of focus, imaging at the focal point or the focus. The focus is right here, right where the beam is the narrowest. So this guy right here is a phantom, a tissue mimicking phantom. And you can see how a lot of the stuff in the phantom is circled. If they ask you, if they show you an image like this, which are circled or labeled or whatever, or they have an arrow pointing to it, if they say which area of the phantom evaluates lateral resolution, you're going to look for right here, these guys. A lot of people will think that lateral resolution is evaluated right here, the pin circled in blue, but that would be incorrect because this is the horizontal registration, and these evaluate the position or location of each pin going across the sector. But lateral resolution is evaluated right here in orange. But that's not the only resolution that's evaluated right here. Axial resolution is also evaluated here. Let me zoom in here. When we're trying to evaluate two closely spaced reflectors side by side perpendicular to the beam is going to come from this way. The beam has to come from this side so that as the beam is coming through, you're able to see the distance between those structures. And the more narrow the beam, like we talked about, the better you're going to see the space between those two structures. And then as we move further down, the pins are getting close together, you can see the space there pretty well, and then right there. And then right here is where you can't really see it that well. It looks like one structure. There's actually two structures, but you can only see one. That means lateral resolution right here isn't the greatest. Right here, you can see the space between these two structures pretty well. Maybe right there. Definitely not here, here, or here. So lateral resolution is poor here, here, and here. Lateral resolution is a ton better right here. So just memorize, get it in your head now that this is the lateral resolution, and this right here is completely separate, completely different. So this diagram here represents the beam. The crystal would be right here. As the ultrasound beam exits the transducer, it will converge. It'll converge to a single point called the focus. This is the narrowest point of the beam. What you need to know, especially for your boards, is that when ultrasound exits the transducer, or when it transmits, we call it the transmission of ultrasound, it will converge. It first converges to a single point. Once it converges to a single point, called the focus, which is the narrowest point of the beam, then it will start to diverge. When it converges to a single point, this is talking about the near field. The near field, or the Fresnel zone, will converge to a single point. When it diverges, we're talking about the far field, or the Fraunhofer zone. So first converges, then it diverges. When we want to improve lateral resolution, the main thing is we want to keep our beam width narrow, because beam width is what determines lateral resolution. When anyone says lateral resolution is the ability to see two structures side by side perpendicular to the beam, we're talking about how the beam will go straight down like this, and the two structures in this plane, so these two structures can be explained in this plane here compared to this plane. This plane here, the two structures, is going side to side like this, and the beam is going straight down. So that's what it means when the beam is perpendicular to these two structures. If we place two structures right here in the near field, what you'll really see is one structure. This is what your image will look like. You'll only see one structure because the beam width right here is larger than the distance between these two structures. What you want is the beam to be narrower than the two structures. If we were to place two structures right here at the focus is where your lateral resolution is the best. This is how your image is going to look. You're going to accurately be able to see two structures as they are displayed. If the beam width is more narrow than the two structures, then you're going to be able to see two structures. If the beam width is wider than these two structures, I'm talking about the distance here. Here's the distance between this side and this side. This is a lot wider than the distance between these two structures. If there are two structures right here, then because the beam width is wider than the distance between these two structures, then we're only going to see. That's the point of using a dynamic aperture, because a dynamic aperture can change the focus at various depths. And yeah, dynamic aperture will improve lateral resolution. So good. They could have a bunch of options that will improve lateral resolution, like a high line density or high frequency dynamic aperture, focusing, whatever. What they'll say in the question is, which of the following will have the biggest impact of lateral resolution, or which one will improve it the most? And you're going to want to look for the beam width. You'll either want to look for beam width or narrowing the beam.